Good morning, class. I hope you had a wonderful weekend, and we wanted to get right back into our chapter 10. It's all about solving systems of equations, using that to introduce matrices, and then seeing a few more things we can do with matrices. Now, there's a lot more that can be done with them. You'll learn that about those in college and everything, but for now, you just wanted to see a little taste of that. As we get on to 10.8, we're going back to the very beginning. We're going back to the idea that we want to solve a system of equations. But whenever we get to 10.8 and a little bit of 10.9, we think, what if our equations are not linear? What if we're trying to solve a system of equations and it doesn't look like this? Okay? What if our systems of equations does not look like that and we just, we're trying to find that specific point? What if instead we've got something a little bit more complex? Maybe we've got one that looks like this and another one that looks like this. Well, if we think about solving a system of equations, just like this one has one solution, because there's one point where they intersect, here we have two solutions. Okay, and we can find out where those solutions are. If we have them on a graph, we can pinpoint where they are, approximate where they are, but if we use algebra on them, we'll be able to find out pretty effectively if we use the same kind of stuff that we've been doing. Now, we're going to go back to the two methods that we used before matrices. That's elimination and substitution. And so we're going to solve this system of equations. If you look at the equations, it's always a good idea at the beginning to write down what types of equations they are. The top one here, and I'm going to use blue to graph this top one, and this is a circle. Okay, it's a circle, x squared plus y squared. We have a center at 0, 0, because it's not x minus 3 or y plus something. That would change the center, but we know where that circle is. And then we have a radius of 25. And that's because 625 is actually 25 squared. All right, so we know that it's a circle with a center of 0, 0 and a radius of 25. The second one, you notice there's no powers or anything. This is just a regular basic line. Okay, it's a line, it's got a slope, it's got a point. Now, if you do a little work on this equation, we shift over the x, multiply by -1, so we can make that y. It ends up being y equals 3x plus 25. And that gives us two main things. Our slope is 3, and our point is 0, 25. Okay, knowing our slope and point, that allows us to go ahead. We could do kind of a quick graph with this. It's going to be a little bit difficult to graph it pretty big. I mean, you could put them both in Desmos perfectly fine, but it won't be too much of a problem here. Since the circle is 25, I'm just going to mark 25 on each point, each axis, 25, and we've got our nice little circle here. Okay, not perfect, but good for the time. Okay, so we got our circle, and then we have our line, and the line goes through the point 0, 25. So it looks like we already know where one solution to the system of equations is, and it's got a slope of 3. So it's going to go down like this. We don't know where the second solution is. It's probably in quadrant 3 somewhere. Not too sure exactly what those details are, but we know it's somewhere around there. All right, so we know that there's going to be two solutions to this system of equations, and we already know where one solution is. Now, let's go ahead and see if we could solve this algebraically. I'm going to rewrite the equations. We've got x squared plus y squared equals 625. And we have, I'm going to rewrite this as y equals 3x minus, or 3x plus 25. Okay, y equals 3x plus 25. All right, so in doing this, you notice we can't eliminate anything automatically because we have an x squared. You can't subtract an x from an x squared and eliminate anything. What we can do, though, is go ahead and substitute. So we're going to do some substitution. Okay. With our substitution, we're going to end up like this. We've got x squared plus 3x plus 25 squared equals 625. Going ahead and just trying to solve this one, we got x squared plus 9x squared plus 75. Wait. Let me make sure you see this. 3x times 25 is going to be 75x plus another 75x plus 625 all equals 625. Subtracting 625 from both sides, going ahead and doing what we can to solve, we're going to end up with this. 10x squared plus 150x equals 0. Factoring out an x from those, we get x times 10x plus 150 equals 0. Now we can also factor out a 10 from each of those, so I'm going to do that. 10x times x plus 15 equals 0. So, what are my x solutions? If we look at that first one, these are two things that multiply together to get 0. So this is going to be our zero product property. So we know that 10x equals 0 or x plus 15 equals 0. X equals 0 or x equals negative 15. Now I told you that there were two solutions. Here are the x's for those solutions. Now if we want to find the y's, we could use either one of the equations. Obviously, the lower one, the y equals 3x plus 25, would be a little bit easier to use. So we're going to plug those in. Y is equal to 3 times 0 plus 25, which is equal to 25. So we end up with these coordinates, 0, 25. And y is equal to 3 times negative 15 plus 25, which is negative 45 plus 25. So y is equal to negative 20. So now we have another set of coordinates, negative 15 for x and negative 20 for y. All right, two sets of solutions, and if you can definitely see, negative 15, negative 20 is right around there. If we square 15, we're going to get 225. We square 20, we're going to get 400. 400 plus 225 gives us our 625. So we can even check it using this equation. All right, using the substitution method, we got that. Okay, the graphical method is what I drew right up here. We were looking for those two quadrants. We didn't know exactly what this one was, but we're sure. And I just didn't fill this stuff out down here. Graphically, or I didn't fill out the substitution method down here, but we did solve it right here. All right, let's do some solution. Let's solve this problem graphically. We got y is equal to x cubed minus x, and we got x squared plus y squared equals 2. So for our first equation, that is a cubic. Okay. it's a cubic function, and it is a typical cubic. We know that x cubed, there's no negative in front of it. If there was a negative, it would go down. This one ends up going up. It's good to know. And if it's a cubic, it's got 3 roots. We'll talk about that in a minute, though. In addition to that, we've got the bottom one. That bottom one is a circle again. Now this circle has a center at 0, 0, and it has a radius of square root of 2. So cubic function versus a circle with a radius of 2. If we do this graphically, let me switch to that. We want to make a big graph. Okay, got a nice graph there. I'm going to graph the circle real quick. Okay, circle's got a radius of 2, so each of these are square root of 2, square root of 2. This one, the y value is negative square root of 2, and here the x value is negative square root of 2 because they're on those negative axes. Okay, so we've got that, and then we have the cubic. Now, cubic, if you remember, just a basic cubic looks like this. But we want to be more specific here. If we're going to be doing it graphically, we want to be accurate. And so we need to take a look at our cubic. And we've got x cubed minus x equals y. We're going to assume y equals 0 so we can get our roots. Okay, so if y equals 0, we've got x cubed minus x equals 0. Factoring out an x, we get x times x squared minus 1 equals 0. And if you remember that x squared minus 1 is called the difference of squares, that gives us two equations, x squared, x minus 1 times x plus 1 equals 0. And that gives us 3 roots. Okay, x equals 0, x equals negative 1, and x equals 1. Okay, so looking at that, thinking about it graphically, we would be like, okay, it happens at 0, happens at negative 1 right about here, and happens at 1. If you draw this graph, you should get something that looks like this. Okay, in shape with those roots, and you can see that it will intersect in 2 specific places, and these places are our solutions. Solution 1, solution 2. Okay, now let's try the elimination method. Can we do an elimination method for nonlinear equations? Now again, it's always nice to start off by just thinking about the types of functions that they are. And so we're going to do that. That first one, 3x squared minus 5y equals negative 3, that is a quadratic. You can tell it's quadratic because it's x squared and then the y is linear. If the y was squared too, it would be a circle, or as you'll learn just a little bit later in another chapter, we would call that, if the y was squared and we've got these numbers multiplied by it, it ends up making an ellipse. But we'll talk about that later. And if we look on the bottom, we've got another quadratic for the same reasons. So if we have 2 quadratics, what's that going to look like? And again, these quadratics, I'm just doing a quick drawing. We're not doing it fully graphically. But let's say we've got one quadratic that looks like this, and another quadratic that looks like, oh, let's change that back to blue. That looks like this. They could, hold on just a second, another quadratic that looks like that. They're going to intersect a few times. We could, if we have some sharp quadratics, that might be a little bit lower. It might intersect 3 times. Most of the time, it's only going to be 2. let's go ahead and see if we can use elimination to solve these. And let me rewrite those equations. 3x squared plus 5. You know what? Let me not rewrite them. What I'm going to do, thinking about using my abilities here, I'm just going to do elimination right here. Well, looking at that, if we want to eliminate something, we can't exactly do it right now because trying to eliminate something, it just won't work. So instead, why don't we multiply so we can end up getting rid of these y's. Okay, we're going to multiply the top by 3. The whole top by 3 and the whole bottom by 5. And that'll get both of the y's to be 15y. And we end up with 3x or 9x squared plus 15y equals negative 9. And 20x squared plus 15y equals, what is 5 times 18? 5 times 8 is 40. 5 times 50 and 40 is 90. Okay, equals 90. All right, so now that we have two y's that are the same, we can eliminate them. Pretty simple. Let me switch colors here. Subtract that, subtract that, subtract that. We're subtracting the whole thing in elimination. And whenever we do so, we end up with 9 minus 20, which is negative 11x squared. And negative 9 minus 90 equals negative 99. Solving for x, divide both sides by negative 11, we end up with x squared equals 9. And so x is equal to positive or negative 3. Okay, so x can equal 3 or x equals negative 3. Which one is, or both of those are correct. Now we just want to find out what our y value is. We could plug it into either equation, just like before. Once we find out our x, we can just plug it into an equation to get the y. I'm going to plug it into the second equation because that deals with a lot of positives, and it's just nice to deal with positives. So I got 4 times 3 squared plus 3y equals 18. 3 squared is 9. 9 times 4 is 36. Plus 3y is equal to 18. Subtracting 36 from both sides, we get 3y is equal to negative 18. Y is equal to negative 6. On this one, we've got 4 times negative 3 squared plus 3y equals 18. Hey, wait a second. If I square negative 3 and multiply it by 4, I get 36. Plus 3y equals 18. Subtracting, dividing, all that stuff, we end up with y is equal to negative 6. And so our two solutions here would be 3 comma negative 6 and negative 3, negative 6. So they will intersect twice at specific places. All right. Can we do this to even other equations? Of course. We can eliminate this one. Let's do it. If you notice, each of these are exponential functions. They're exponential functions with the natural number e. And it's pretty nice. We can already eliminate the e's by just adding both rows. And so we eliminate those. I can just put 0 down there. Plus 7y equals 7. Y equals 1. So now that we know that y equals 1, let's find out what e to the x equals by plugging it in. E to the x plus 2 times 1 equals 5. So e to the x equals 3. How do we get rid of an exponential function? Pull out the exponent. We use the logs, and specifically we use the natural logs. This is the inverse function. So we would use the natural log of e to the x is equal to the natural log of 3. And as you know, the natural log of e, the x would go out in front using the power rule, and the natural log of e is really 1, so it ends up being x is equal to the natural log of 3. And this gives us our solution. Now, the natural log of 3 does have a decimal approximation, but natural log of 3 is the best way to write the number, and we end up with a point ln of 3 comma 1. Now, these are two exponential functions, and I do want you to kind of see what they look like real quick. If we think about these two functions, we've got one that looks like this, and we've got another one that looks like this. Let me think just a second. Oh. Okay. And where they intersect, the y value will be 1, the x value will be the natural log of 3, which is going to be just a tiny bit over 1. All right. With that said, I'm going to bring this video to a close. Hopefully that helps you to understand how we can solve systems of nonlinear equations. All right.